Okay, Assalamualaikum and very good afternoon to all of you. So we continue our class with the half wave rectifier. Okay, control half wave rectifier. So as usual, we will continue with this first with the R load, which is very simple R load here. So right now, so this is a control half wave rectifier, meaning that we replace the diode with the SCR. Okay, so we have replaced the diode with this what I call SCR or Thyristor. Okay, so by using this control half wave rectifier, what we can have is actually we can have a variable output voltage. Okay, variable output voltage. So in order for this circuit to turn on, okay, this SCR, there are two conditions that must be met. Okay, the first one, you need to ensure that the SCR must be in forward bias. Okay, and then the second condition, you need to supply or apply a triggering signal, which is a IG current, to the terminal gate for the SCR. So as you can see here, we have this one is the voltage source waveform, and this one is your V output waveform. While the third waveform here is actually the triggering signals that apply to the gate terminal. So as you can see here at this part, okay, at this part of the V out, even though the SCR is in forward bias because the polarity of A anode is much more positive compared to cathode, okay, but you can see that even though it is forward bias, it will remain off. Okay, it will remain off like this. Okay, why? Because you haven't give a triggering signal to turn on the SCR. So that's why it remains off. Until you give a triggering signal, a very short triggering signal at alpha, at a location alpha angle, okay, then you will see that uh, the SCR is turned on, and then it will, as you can see, when this one is turned on, meaning that V out is equals to Vs. So it will follow the shape of the Vs until pi, where right now the polarity is changed. So this one will become negative and this one will become positive, meaning that the SCR is in reverse bias. So it will automatically turn off. Okay. So this alpha, you can actually vary the location of the alpha. Okay. So depending on the value of the alpha, you will have a different shape of V out. Okay. So if your alpha is location here, so meaning that it will triggering at this point and then it will follow the shape of the Vs. Okay. So you will have a different area to get your V out average. Okay. So because V out average is depend on the closed area under the graph here. So meaning that by adjusting the value of alpha, so you will have a variable V out. So V out average calculation, you can use this formula. So 1 over your period is 2 pi. And then your function of the voltage is from alpha to pi, okay? From alpha to pi. So you integrate from alpha to pi. And then the function of the voltage output, which is Vm sine omega t d omega t. So you integrate this. So you will finally obtain that you will have Vm over 2 pi multiplied with 1 plus cos alpha. And as you can see here, you have cos alpha as the variable. So meaning that to get V out average, you can either adjust the value of the alpha here to get the V out average that you required. Okay. So if the alpha is 0, meaning that there is no delay in the triggering signal, meaning that alpha is 0, meaning that you trigger at this location, 0 degrees. Okay. So meaning that when this SCR is forward biased and then you haven't delayed the triggering signals, so it will have a shape like a diode rectifier. Okay. So when this alpha is 0, so when you substitute alpha 0 here, so you will obtain Vm over 2 pi 1 plus 1, which is you have Vm over pi. Okay, Vm over pi, which is similar to the diode rectifier. Okay. So meaning that when alpha is 0, so the SCR, the SCR rectifier behave like a diode rectifier. The same case goes to the RMS voltage. So this is the RMS equations, and then it has been simplified like this equation. So you can use this equation to calculate your V out RMS. And of course, if you set alpha is 0 here, okay, and then here, so you will obtain that your V out RMS is equals to Vm over pi. Vm over 2, which is same with the diode rectifier. Okay. So actually, the advantage of using SCR is that you will have a variable output voltage. That is the only advantage. Okay, so this is example 3. Sorry for this sketch here because I accidentally save it, okay, in the previous class. So actually this one is the solutions lah. Okay, so source is the sinusoidal, which is a 240 volt RMS at a frequency 50 hertz. The load resistor is 150 ohm. Okay, and then the delay angle is, which is your alpha, is 30 degrees. Okay, so delay angle, or sometimes we call triggering angle and so on. So but you need to know that this actually delay angle is referring to the alpha. So alpha is 30 degrees. So determine the average output voltage. So I think this one you can directly use the equation. So Vm over 2, 1 plus cos alpha. So your Vm is your 240 volt RM, 240 multiplied with square root 2. You need to multiply with square root 2 over 2 multiply with 1 plus cos 30 degrees. So you should get 316 volt. Okay, 316.6. 316.6. Is it correct?
Check, doctor.
Is it correct? Okay. So if correct, then we move to the B, the average load current. So the average load current, the equation is I out average equals to V out average over R load. So which is a very simple one. So 316.6 over 150 ohm. So you should get 2.11. And then for the average power output, you can either use this one, V out RMS, multiply with I out RMS, okay? Or this one, I out RMS, multiply with R load, okay? But since we have already calculated, okay? Oh, sorry, we haven't calculated the I out RMS. Okay. So you can use either these two equation, okay? Sorry? Is that for the power?
3 at 4.
Can I hear you, Sam?
Can you?
3 at 4.
384,
Yeah.
the power. Okay.
Yeah.
Which equation that you use, the second or the first one?
Both is 3 at 4.
Or 384. So can you share with us your V out RMS? V out RMS? V out RMS. Can you share with us the value? You can use this equation, right? V out RMS. Or any others that can share with us the V out RMS that you have calculated, so that the other student can check, double check. V out RMS. Use the equation Vm over 2 and then multiply with square root 1 minus alpha over pi. So meaning that your alpha, you need to convert into radian. Okay. So 30 over 360 multiply with 2 pi. So you should get 0.52 radian. Okay. So this one, 0.52 radian. So 1 minus 0.52 over pi plus sine. If not mistaken, it's 167 volt. Is it correct? I don't know.
167.
167.
Yeah.
Okay. Okay. This pi, this alpha, you need to convert into radian. Okay, before you divide by pi. So the conversion is like this. Okay, so you should get your alpha in radian is 0.52, and then after that you can divide by pi. Okay, so the whole this is actually a whole part. So you should get 167 volt. And from there, use this equation to calculate the I out RMS. So over 150. So you should get 1.115 amperes. Okay. Hmm. But if I use that, my answer is not. My answer should be the power absorbed should be 186 watt. So I don't know. Based on these values, so the power should be 186 watt.
How get the V for RMS? The sine 2 alpha is used angle, right?
Sine to alpha
Yeah.
is 60, right? 60. So sine 60. So that's why I want to double check because I just key in the calculator.
And then
So
VM.
what is your value? V out RMS, Sam?
Doctor, I want to ask about the VM is 240, right?
VM is not 240. You need to multiply with square root 2.
Oh, okay.
This one 240 is a VRMS.
Okay.
So VM should be 240 multiplied with square root 2. Okay. Sine 60 over 2 over pi plus 1.52 over pi. Plus 1.3.
It's 186.
Hmm?
186.
186. The power.
Yeah.
Okay. Okay. So meaning that V out RMS is correct. 167 volt. Okay.
Yeah.
Okay. So because you need to be careful here. Sometimes, yeah, because the conversion and so on. Saya pun main buat laju je ni, so tak pasti betul tak betul. So that's why I want you to double check. So I think the value is correct. So V out RMS is 167 volt, and the I out RMS is 1.15 amperes, which is by using this formula. Okay, the I RMS. This equation is very simple. The current and the voltage relationship is very simple and straightforward. Okay, because your load is a resistor load. Okay, so meaning that to get the I out average, you just use V out average over R, and to get the I out RMS, just use V out RMS over R. So just like that, straightforward, because the load here is a linear load. Okay. But for the inductive load, which is you have R and L, so you cannot use this formula. Okay, because the relationship between voltage and current is no longer linear. Okay, can we move to the next example? So example 4, which is bracket design, meaning that it is a reverse. Okay, so right now, the source is given 230 volt RMS. Okay, so highlight this one. This one is RMS. So meaning that your VM you need to 230 volt multiply with square root 2. Okay, so and then the load resistor is 80 volt. But and then 80 ohm, and then it give you the V out average. Okay, right now it already give you the V out average, which is 100 volt So determine the thyristor delay angle. So which is the alpha. What is the alpha? So use this formula 100 volts over Vm over 2 pi 1 plus cos alpha. Okay. So your Vm should be 230 multiplied with square root 2. So 325. So just use that. Then you will obtain your alpha is cos inverse 2 pi multiply with 100 over Vm. Sorry. Inverse cos 2 pi multiplied with 100 over Vm minus 1.
Doctor, I calculate is 21.05.
21.05 degrees. Okay. So let us check. So multiply with pi over 325 minus 1. Then inverse cos. So 21 Okay, good. 21.05 degrees. And the average load current is simply VI out average over V out average over R, which is V out average has been given 100 volts. The resistor is 80 ohm, so this one is 1.25 amperes. Actually, in this chapter 1, okay, most of the questions, especially for your test and final exam, will be more towards on sketching. Okay, sketching. Because for this linear load is okay. We can give calculation based questions. But when the question involve on the inductive load, so all the question will be more towards on the sketching of the waveform output. Okay, so you need to be more concentrated on that. Okay. Because it involve for the inductive load, it involve non-linear current, so it's quite difficult for the student to calculate the waveform equations. Okay, especially when the current is non-linear. Okay, so I think we good on this. So let's move on the next one. Okay, so this one is the RL load. So when you involve, when the load is actually inductive load, so definitely the current and the voltage relationship will be no longer linear. So so this is actually the output waveform, sorry, the input waveform here. It's a cyclic waveform. And then this one is the output. So actually same. Actually the operation, the concept is actually same. But since we are using SCR instead of diode, so we have what we call the delay angle here, alpha. Okay, it depends on the location of the alpha. So you will have a 0 voltage output here until you trigger. Okay, until you give a triggering signal, then the SCR will turn on. So when this one is turned on, so V out is connected to the VS. So that's why you will have the shape of the V output, same like the VS. And then until at pi. Okay. And then from pi to beta, okay, from pi to beta, you will see that you have the voltage output still remain on here. It's still meaning that this SCR is still remain on. Why it is remain on? Because of the inductor energy storage here. The energy stored inside the inductor, it need to discharge. Okay, so it need to discharge. So it force. So the current will flow, and then it will force the SCR to remain on. So when this SCR is remain on, so the V out is still connected to VS. So that's why you will have a waveform of the VS appear at the V out until the energy inside this inductor already finish discharge. Okay, so where the location where the energy is finished discharge is what we call extinction angle, beta. So right now alpha is what we call a delay angle, and beta is what we call extinction angle. Okay, sudut kepupusan. Okay, and you will see that the current is also, as you can see, is charging during the positive cycle. So it will start charging when the SCR is on. Okay, and then charge, and then until at the when it come into a negative from pi, after pi, you will see that the current is actually discharged. Okay, going down. So meaning that this current is starting to discharge until the current is 0. So actually the energy inside the inductor is proportional with the current. So when the current is reducing, so meaning that the energy also reduce. Okay, so actually the principle is same with the with the diode. The only thing that different is the firing angle. Okay, so and then I think this one is similar. So this one is actually how you derive the output current equation, which is same with the diode. The only difference is that we have alpha. Okay, alpha as our delay angle here. So I think we can move forward. Okay, so this is actually the summary. So the alpha. So this is the current waveform for the RL control half wave rectifier. Okay, so I think the difference is at this part, because for the diode you have only sine theta, right? But for the SCR you will have this one, alpha minus theta, and also at this part. I think for the SCR you have only omega tau, omega t only. Okay, negative omega t, but right now you will have negative alpha minus omega t. So that is the only difference. Okay, and then this waveform current is appear only from alpha to beta. And also for the beta, the values of the beta cannot be solved manually. Okay, it can only be solved by using numerical analysis. Okay, so I don't know, for the numerical analysis, who is the lecturer for, maybe if you still remember, numerical analysis? You don't remember? Because we just know that one of our mathematics lecturers that usually teach this course, numerical analysis, which is Tuan Haji Ismail Kamis, just passed away, I think yesterday or past 2 days ago. He is also my lecturer during my graduate study in UTM. Okay. So, and then this is the average DC output voltage. So you need to integrate it from alpha to beta. So this is your V out average, okay? From alpha to beta. So you will have Vm over 2 pi cos alpha minus cos beta. Okay. So okay. Why? So you will have like this. So meaning that you have waveform. Okay. So V out average, okay, is this one. Okay, meaning that is actually you need 1 over 2 pi and then integrated from alpha pi Vm sine omega t plus pi to beta negative Vm sine omega t. Okay, you have two portions from alpha to pi. Okay, you have a positive here, and then another portion is from integrate from alpha from pi to beta, which is negative Vm sine omega t. Okay, and finally you will obtain this one, Vm over 2 pi cos alpha minus cos beta. Okay, and then the average current, as usual, this one shows you 1 over 2 pi and then integrated from alpha to beta. And then this current is actually a non-linear current, which is this one, okay, which is Vm over Z and then sine omega t minus theta plus blah, blah, blah. Okay, so you need to integrate that. But usually we will not a student on this. And then the RMS current and then the power absorbed by the load. Usually we use this. Okay, it's better to use this formula. Okay, so I recommend that to use this formula. Okay, for the to calculate the power for the rectifier circuit. Okay, and then example 5. So the source is 230 volt RMS. So meaning that you need to calculate Vm. So square root 2 multiply with 230. So this one 325. And then it gives you the values of resistor is 80 ohm and the inductor is 60 millihenry. This one frequency is 50 hertz. Okay, and then it gives you the value of the average output voltage. So V out average is 100 volts. And then it also gives you extinction angle, which is your beta at 200 degrees. So determine the Thyristor delay angle, which is, I think, very straightforward. So you can use this formula, V out average Vm over 2 pi cos alpha minus cos beta. So this one is 100, 325 cos alpha minus cos beta. So cos 200 is so positive 0.93. So this one Berapa So I think it should be around maybe
6.49.
6.49
49.
degrees.
Yeah.
Very small. The alpha. Ada yang dapat sama? Anyone got the same answer?
Doctor, I think will be different because the 0.93 I take 4 decimal places, which is 0.9397.
I know.
Yeah.
So 6.4 something lah.
64.72.
6.72. Okay. I think it's okay lah because the different for example the cos beta is quite what you call decimal tu is macam is very is too small. So that's why I think if this one is acceptable, this range 6.49, 6.72 is okay. Because the difference is very small. Okay.
Yes.
So I think it's okay, acceptable. Okay. And then I think the second one is straightforward. The average output voltage if the thyristor delay is angle is set at 20 degrees. So just substitute the values 325 over 2 over pi and then just multiply with cos 20 minus cos 200. So 97, right? 97 volt. The V out average. Okay, I hope you all get the value 97 volts.
Yes.
The beta is still remain 200 degrees.
Yeah, doctor, is
97. Okay, thank you for that confirmation. Okay, so before we proceed with the next subtopic, so I just want to show you something about this location of beta. So as mentioned before, this beta location is actually the point where the energy inside the inductor is already fully discharged, right? So meaning that this beta location depends on the size of the inductor. Okay, so if the inductor is very big, okay, so the position or the location of beta might be far away, maybe at this point. For example, okay, maybe at this point it will fully discharge. Okay, so it depends on the inductor size. So if the inductor size is small, then your beta will be very, very near to the alpha. Okay, but if your inductor size is very big, you will see that your location of beta will be very far from the alpha, from the pi. Okay, sorry, from the pi. It depends on the size. Okay, so meaning that if it is larger, meaning that the time required to fully discharge the energy inside the inductor will take more time. Okay. Okay, so next we move to the next subtopic, which is still half wave rectifier, but the load right now is the RL with a load, with a source. Okay, so right now your load is actually RL with a source, meaning that you have R, and then you have inductor, and then you have a DC source. So this is your V out. Okay, so meaning that your V out is from here to here. So this one is your V out. So what type of the load that has this type of characteristic? Okay, this one is actually you can see from the DC motor. Okay, so that's why actually this one we actually this part is not included in the syllabus, but since our PBL lab, the power electronics lab, we have a experiment DC motor using rectifier, then I think we should put some theory, okay, in the our power electronics syllabus. So this model is actually, this load model is actually representing the DC motor. Okay. So DC motor, as you can see, is actually use a DC power supply. So that's why we have a rectifier here. So this one is your AC input, and then we rectify using diode, and then supply to the DC motor. Okay, so inside that circuit, so the diode will remain off as long as the voltage of the AC source is less than the DC voltage. So right now, as you can see, this one is your voltage AC. The black color here is your AC source. And this brown color is your DC load. Okay, is your DC source at the load. And as you can see here, this is the current. This is your I output. Okay, so the diode will remain off until VAC is larger than VDC. So when VAC is larger, then you can see that the diode is on, and then it will start, since you have inductor, so meaning that the current is charging, okay, and then at some point it will start discharging at location, and then it will stop, at beta. Okay, so that is the only difference. The only difference is that the diode, okay, right now this diode at this part is actually VAC, and then at this part is actually VDC. So this diode will on when VAC is larger than VDC. Okay, then the diode will on and the current will flow. So that's why we have a current flow here after this point. Okay. And okay, do not confuse. We have another what we call conducting angle, but also represented by alpha. So the conducting angle, the angle where the current is start to flow, or the diode is start to turn on, is you can just use this formula, Vm sine of alpha is equal to VDC. And from here, we manipulate. So we VDC over Vm. and then inverse sine. Okay, so that is alpha. So alpha is actually this, for this example, is referring as a conducting angle, the angle where the diode is start to charge, okay, or start to turn on. And then this is the KVL here. I think this one is actually more towards on the current derivation. So the complete, so this is actually the current, which is a non-linear current. Okay. So we have same, we have this part Vmz sine omega t minus theta. Okay. And then, but we have some addition, which is negative VDC over R. Also, and then we have also here A. So, but A is not solved. So we, how to solve A? So we set the I is equal to 0. I when the location of alpha is set. So we set to 0. So finally we'll obtain the values. Okay. So, but this one is not, will not be in your test or your final exam. It is just for the information that you need to know when you are conducting the experiment for the DC motor using half-wave rectifier. Okay, so this is just a guideline for you for the experiment. Okay, and finally, so this is the current. The green one is the current, and finally this one is your V out. Okay, so this waveform is your V out. So as you can see, we have before the diode conducting, the output is VDC, and then this is when the diode start conducting, the current start flowing. The V out is actually equals to the VS. Okay, and then as usual, until beta, where the energy stored inside the inductor already finished, then it will stop to discharge, and then it will remain off. Okay, the diode will remain off, but the V out is VDC. Okay, the V out value is VDC value here, and then it will repeat again and again in a cyclic manner. Okay, so we have here the difference is actually we have DC shift here, which is equals to your VDC. Okay, so this one is your zero voltage. This one is your zero. So that is the only difference from the RL load and the RL with DC source. Okay, and then this is the average current formula, and then the RMS current formula, and then the power calculation associate, which is same, this one, and also the power factor. So this power factor is general, okay? So you need to use this power factor. As usually when you want to calculate the power factor, always use this formula. The P out over the S source. Okay? The P out, which is the power absorbed by the resistor, and then the S source is the apparent power supplied by the source, which is the VS RMS, and the current source RMS. Okay? And then for this one control by using the SCR, same. I think the principle is same. So this one is your V out. Okay, conducting begins when a gate signal is applied to the SCR, but provided that the SCR is already in the forward bias. Okay, so I think same. The only difference is that you have the minimum alpha conducting angle. Okay, this one you can refer when you are conducting the experiments lah. Okay. Okay, the analysis of the circuit is actually very similar to the uncontrolled rectifier with the RL load source. The only difference is the selection of the conducting angle alpha. Okay, the angle value must be within the allowable range, which has been shown in the slide. Okay, I think any question before we take a break and then we move to the full wave rectifier? So we take a break around maybe 10 minutes. So right now it's 11:54. So we will come back at 12:05 lah. 12:05, okay? So you can exit this room first and then at 12:05 we come back. Okay, thank you very much. We meet again at 12:05. Okay, so we continue. Chapter rectifier, single phase, full wave rectifier. Okay. So we have already learned about on the half wave rectifier, which is the control and uncontrolled. So right now we go for the full wave. So under this full wave, we have two type of circuits, which is that we will go explore, which is the first one we call bridge circuit, and then the second one is center tab circuit. So actually this center tab circuit we are using a transformer, okay, to provide the electrical isolation between the source and also the load. Okay, so and then under these two topologies or circuits, we can divide two other circuit, which is the control and also uncontrolled, and the same case also goes to the center tab, which is the control and uncontrolled. But actually, the only difference is on the operation of the circuit. But in terms of the equations, for example, the V out average, I out average, V out RMS, I out RMS, and also the P out, which is the real power calculation, the equation is actually similar. The only difference is in the circuits and how they operate. So we go first, the what you call the bridge. Okay, the bridge full wave rectifier. Okay, so circuit below here shows the what you call the full bridge rectifier, where we have 4 diodes, and then the numbering of the diode we arrange like this. Okay, D1, D2, D3, and D4. Okay, we arrange that because they are actually work in pairs. For example, for the first half cycle, which is the positive cycle, okay, we have the right now the voltage source, we have positive and negative cycle, right? So this one is what we call positive and this one is negative cycle. So positive cycle, D1 and D2 will conduct. Okay. Why they are conducted? Because it's actually depends on the circuit. So right now, as you can see, the polarity is like this, positive, negative. So right now, since this is a positive, okay, so the anode is positive compared to cathode, so D1 will turn on. Okay, D4 is off. Why? Because as you can see, this point, okay, is actually positive, so meaning that this one is also positive. So meaning that the cathode is more positive compared to anode. So D4 is off. And then why D2 is on? Because as you can see, the cathode is actually connected to the negative terminal. Okay, so meaning that the cathode is more negative compared to anode. So that's why D2 is on. And D3 here is off. Why D3 is off? Because as you can see, this point also, this node is connected to the anode of the D3. So this one negative, so that's why D3 is off. So diode is on because of the forward bias of the circuit. So it depends on the fault bias of the circuit. So for positive cycle, D1 and D2 will turn on. And since the load is a resistor load, so meaning that your current will be also like this. So this is your I output. Okay. And then for negative cycle, for the half negative cycle, so right now the polarity has been reversed. So this one is negative and this one is positive. So right now we see that since this one is negative, so meaning that this one D1 is off. Okay. And then this node is connected to D4 negative, the cathode. So meaning that D4 will turn on. This one positive. This one is positive. So meaning that this D3 will turn on and D2 is off. So D3 and D4. So the current will flow through D3 first and then go back through the load and then go back to the source through D4. Okay. And then the load is a resistor load. So meaning that you will have this current output waveform. So as you can see for the full cycle, you have full rectification. Okay, so this one is your V out and this one is your V out. This one is your V out. Okay, so full rectification. Okay, so as you can see here, so this one is your V source and this one is your V out. Same case to the current output. You have a full rectification. Okay. So this one, please, I think you need to change this. One must be also positive. Okay, positive. Both both half cycle must have a positive polarity. Okay, positive magnitude because it has been rectified. Okay. So I think that one is clear. Okay, so let's move on the what we call the this one reverse bias voltage for non-conducted diodes is equals to the peak value of the source. So this reverse bias voltage, this is actually referring what is the V blocking, which is referring to the V rating of the diode, right? So I have already explained about the V rating of a device. So actually the V rating of a device for the power electronics circuit, okay, the transistors and the diode or the SCR, the V rating for that device is always referring to the how much voltage that it need to block during their off state. Okay, during their off state or non-conducting period. Okay, so if you see this circuit, okay, so this circuit, when D1 is turned on and D2 is turned off, D4 and D3 is off, okay, is off. So what is the voltage? What is the voltage rating for this diode? Okay, what is the, or what you call reverse bias voltage that need to be sustained by this diode? For example, D3 and D4. Okay, so let's see how do we calculate that. So let's see this KVL, this closed loop KVL. Okay, this is how we determine what is the V rating. Okay, so right now, if you put your multimeter here, you will see that it will give you the voltage equals to your Vs, right? So this one is your V rating. So meaning that you need to buy a diode that at least equals to the value of the V source, the maximum value of the V source. If the maximum value of the source is 300 volt, then you need to buy the diode that has the rating at least 300. You can buy 400 volt, 500 volt. That's no problem. Okay? Okay, the minimum should be equals to the V source. Okay? You can also buy 1 kilovolt diode. You can buy 1 kilovolt or 2 kilovolt or 3 kilovolt diode. Okay? But as you know, when you buy a diode that has higher rating, the cost will be very, very expensive. Okay? So it will be what you call a wastage of a money. So we want to optimize, okay, the design, the cost, and so on. So when we want to design something, so we need to choose, we need to have some analysis on what is the minimum voltage rating for the diode for my application. For example, I'm using the voltage source 300 volt. So based on this analysis, so the minimum rating should be 300. So for precaution, so I maybe use a 400 volt rating diode. So no need to buy 2 kilovolt or 4 kilovolt diodes. Okay, so it's waste of money. Okay, so this is actually how we determine the V rating. So this reverse bias voltage is actually referring to the V rating or V block. Okay, V blocking. So reverse bias voltage. So this one is actually must equals to, at least equals to the peak value of the source. Okay. So the same case for the negative cycle also, I think it will be the same. So for the D2 and D1, when it is open, so the same rating also. Okay, so for this circuit, for full bridge, the rating of the diode, the rating voltage for the diode must equals to the voltage source. So this is a very important point here. Okay, and this is actually the waveform that shows the voltage across the diode. Okay, this one is the voltage across D1 and D2. So this is the voltage. And this is the voltage across the diode for D3 and D4. Okay, so as you can see, for the positive cycle, so D1 and D2 is on. So, and then we consider the diode is ideal. So meaning that there is no voltage drop. Okay, there is no voltage forward drop. So 0. But as we can see, D3 and D4, there will be a voltage blocking. And the voltage blocking should be at least, the rating, okay, should be at least equals to your V source. And for the negative cycle, D3 and D4 is on. So that's why you have a 0 voltage here, 0 voltage drop. Okay. But you will see that there is a voltage blocking at D1 and D2. Okay. And then this is your output current. As you can see, we have a continuous full rectification for every half cycle. And this one is the current across D1 and D2. As you can see, for the positive cycle, we have the current flow, but negative cycle 0, because for the negative cycle, D3 and D4 will take over the current. So the I output is actually the summation of these currents. Okay. And the last one is the I source. So as you can see, the I source is purely sinusoidal. So there is one advantage of this full wave rectifier, where you will see that your I source is still remain sinusoidal. If you look back at the half wave rectifier, for example, a very simple diode, and then you have a resistor here. So this one is your I output, and this one is your I source. So if you have your load is a resistor, I think your I output should be like this, right? For the half wave. And what about IS? Since I out is actually equals to IS, right? Because we have a single loop here. So I source should be equals to IS. So meaning that you will see that your I source is also is equals to your I output, which is not a sinusoidal. It's actually a what we call distorted sinusoidal. We have only positive current, but there is no negative current. Okay, so in terms of the power quality at the up input side, the TNB supply, so it looks that uh, the power quality is very low. Okay, very low. This is not very good. Okay, because the TNB side, the supply side, they want the voltage to be sinusoidal and the current should be sinusoidal and must be in phase. That is the top requirement for the power quality. Okay, but as you can see here, for the half wave, the I source is totally low quality. Okay, because it is not sinusoidal. But when you use a full wave, you will see that the Vs is still sinusoidal, yes, and then the I source is also still sinusoidal. So meaning that in terms of the power quality, full wave rectifier is much better to be used inside the for the AC to DC conversion. And then, so this is the output voltage. So if you recall, for the half wave, your V out average is Vm over pi, okay? Vm over pi. But for the full wave, it's actually 2 times of the Vm over pi. So it is logic because we have uh, output at both cycle, okay, both half cycle, positive and negative. So that's why we have the V out average is 2 times much higher than the half wave. Okay. And then for the DC current, so since this is a resistor load, so directly you can obtain your I output average, okay, is equals to V out average over the resistor, or V out average is 2 Vm, right? 2 Vm over pi, so multiply with the resistor. And the power absorbed by the load, so I think it's better to use this one, okay, I square RMS multiply with R. And the power factors. So the power factor is 1, okay, unity. Because as you can see in this waveform, the voltage and current are both in phase. So the power factor is unity. So that is the most advantage, the best advantage of the full wave uncontrolled rectifier. Okay, so if you are being given a choice which one that you want to use for the rectifications, so please use full wave rectifiers instead of the half wave. Okay, because it didn't distort the power quality. at the input side. Okay, this one is the second topology, which is what we call the center tab rectifier. So the center tab, the name come from the use of the center tab transformer. Okay, we use this center tab transformer. Okay, so how it is operated? So positive, negative. So this one. So when it is positive and negative, so you have this one positive also. The polarity is like this, positive, negative. Okay. So as you can see, the polarity. So based on this, so the diode will turn on. Okay, and then diode 2, D2 is actually turned off, right? Because it is reverse bias. Okay, so reverse bias. So the current will flow, ID1 will flow here, and then go back to the load. Okay, so right now your I output should be like this, and also your I output also, V output also will be like this. Okay, and then when it is reverse, negative polarity, which is this one, negative, and then this one positive. So this one will become negative, positive, so negative and positive. So definitely this one, D1 will turn off and D2 will turn on, and the current will flow inside. Okay, so the current will flow, and then you will have I output still have a current flow. Okay, so this one pi, so 2 pi, and the V out is also same, which is equals to, the magnitude is equal to Vs. Okay, and then the V out average is same, 2 Vm over pi. Okay, and I out average is also same, which is V out average over the resistor. Same. The only difference is in the circuit itself. Okay, and the operation. So referring to the center tab, comparing center tab and also full wave rectifier, the center tab has one advantage because it has a isolation, electrical isolation between the load and the source. So meaning that if anything happen at the load, for example, short circuit and so on, so we have secure the source. Okay, we can secure the source from damage. So that is the one advantage. The only disadvantage of this center tab compared to the full wave is that the rating, okay, the rating of the diode used, even though, okay, right now the advantage is actually isolation, and then the second advantage is that it use fewer components. Okay, it use only 2 diodes, while for the full bridge it use 4 diodes. Okay, but the only limitation of this center tab is that the V rating is twice from the V source. Okay, if compared to the full wave, the V rating is equals to the V source. But for this center tab, when you want to use center tab, so you need to make sure that the V rating for the diode should at least twice of the voltage source. So how can be the V rating of the diode twice from the source? So let's see. So when it is a positive cycle here, positive, negative, so meaning that D1 is turned on and D2 is turned off. Okay, D2 is turned off. So right now, what is the V rating for D2? So because V rating is always referring to the diode, is to the voltage blocking. Okay, so what is the V rating? So Okay. So the diode here, so the rating is actually, if you see this one is actually on. Okay. So you have two voltage here. When you tap here, voltmeter here, you will have that you have V out and Vs. So this one is actually V out 1 plus Vs, which is V out 1 is when it is turned on, it is Vs. So, and then plus Vs. So, meaning that you have two Vs. So, your V rating should be equals to 2 times of the voltage supply. Okay. So, this one, usually center tap is actually the ratio is 1 over 2. Okay. Because, and then 1 over 2, and then you split into 2. So, that's why it's actually still Vs. So, this one is 100 volt. So, this one is also 100 volt. Because it's split into 2, even though it is 1 over 2. Okay. So, meaning that if your V input is 100 volt, so your V rating should be, okay, this one is 100 plus 100, so 200 volt V rating of the diode. Okay. So, this is the waveform associated with the center tab. So, I think this one also need to be corrected. So, it should be positive. Okay. Should be positive. So, all the half cycles should be positive. Okay, and then as you can see, this one is the voltage blocking, okay, voltage across the diode. So as you can see, the diode when for the positive half cycle is turned on. So that's why there is no voltage drop. We consider ideal case. But for the negative cycle, it off, and then the voltage appears at the diode is equals to 2 times of the voltage input. Okay, and the same case goes to the second diode also. And same case also for the current output, which is you have you need to sum up ID1 and ID2. So ID1 plus ID2 you should equal to I out. And for the I source, same with the full bridge, you will have a full sinusoidal. So which is very good in terms of the power quality. Okay, so I think this one, the equation is actually similar to the full wave bridge. Okay, maybe we do some exercise. We have 1 and 2 before we proceed. This one maybe on Thursday we will proceed on this full bridge with RL load. Okay, so example 1. Any question while we do this example 1? Any question on this? Okay, so we can proceed to example 1. A single phase full wave bridge rectifier has a resistive load and a source of 120 volt RMS. Oh, determine the source peak voltage. This one quite easy lah. Okay, so quite easy. So just square root to 120 volt. Ini kalau masuk soalan final, maka bonus. This is a bonus mark. 169.7 volt, okay? And then the average load voltage, so 2 Vm over pi. 2 multiply 169.7 over pi. So which is very straightforward. The average current, I out average. So V out average over the resistor. So 169.7 multiply with 2 over pi. So 108. So this one 6 amperes. Okay, can we move to the next example? So example 2. So example 2, a single phase rectifier has a resistive load 25 ohm. Determine the average current, the peak reverse voltage of the diodes for each of the diode for a bridge rectifier with an AC voltage. Okay, for number 1, so I out average is square root 2 multiply with 120 volt. Okay, this one is your VM. Okay, multiply with 2. 5 over multiply with the resistor 25. Okay, 4.32 amperes. And for the V blocking lah, we call this one V blocking. You can also use a V peak reverse is equals to negative square root 2 multiply with 120 volt RMS, which is 169. So that is the V rating for each diode that you must buy. At least 169. And inside the market, maybe there is no 169. They may have a 200 volt or maybe 250 volt or 170 volt. So please choose the minimum. Okay. Because as an engineer, so usually when you are dealing with a project, so they are always want to cut costs. Okay. So to cut the cost, you need to make sure that your circuit is optimized. So meaning that the rating of the circuits, okay, for example, the semiconductor and so on, should be at least meet the requirement of the circuit to operate. Okay. Meaning that saya boleh beli je apa-apa yang mahal kan. Tapi the cost will be very high lah. So it's not optimized in terms of the cost. So that's why in your final year project, in for example thesis and so on, they require you to calculate the cost, okay, the development cost, because right now all the funding is the big important big part in terms of running the project. Okay. So the second one, a center tab transformer. I think this one, the I out average, use the same equation. There is no different. the answer should be same, 4.32 amperes also. But the V blocking or V peak reverse should be twice of 169 volts. Since you are using the same source, so around 340 volts. So meaning that you need to find a diode with a rating at least 340 volt. And whether to choose center tap and bridge rectifier, which one you want to choose is depends on the application, because in design there is no wrong and there is no correct design. Okay, it's up to the engineer's decision. We as an engineer, we decide what we want to do, okay, to make sure that the system is operated as optimized as possible with a very lowest cost involved. Okay, so whether to use center tap and full bridge, it depends. If you are more towards on the system or the product to be mobile and very lightweight, don't use center tap, because the center tap you have transformer. So that transformer is a line frequency transformer, a 50 hertz transformer. So it's very bulky and it is very heavy. Okay, so you need to use full bridge. But the disadvantage of that, you don't have any electrical isolation. Okay, that is the trade-off. Okay, so that's why I said in design there is no correct design and wrong design. It depends on the application, and you need to actually able to see which one is good. Okay, so because your priority is to have the product to be mobile, so you need to sacrifice something. Okay, and if you are more towards on the safety side, your product should be in a very your product is very critical, should be in a very safety side, then you need to have some isolation, then you need to use the center tap rectifier for that. Okay, I think that's all from me. Actually, the model that we use, the load model, which is the resistor, the inductive load, and then the RL with DC load, is actually all the loads that represent the actual load. For example, the resistor, you can see is actually represent the bulb, represent the bulb, and then for the RL inductive load, it represent some things like the induction cooking and so on. Okay, while for the RL with the DC load, DC source is actually represent a DC motor and so on. So all this RL representation, all this load representation is actually represent the actual circuit. Okay, the actual load actually. Okay. So actually we have another one load, which is what we call the RC load. Okay, so you have a what you call rectifier here, AC to DC. So you have a RC load, but this one is not covered in the syllable because it is very time consuming. Okay, and this RC load is actually represent a battery. Okay, it can be represented as a battery. Okay. So I think that's all from me. So we meet again on next class, which is on Thursday. And for your information, so I have received a new timetable with a classroom. Okay, just for your information, our classroom for the face-to-face will be at P19, our new building. I hope you still remember the new building. Where is the new building? P19, and then but the highest one, the top level, BT6. Okay, so we meet you again on after Raya, and then for those who are not not in Malaysia, so I think you have been given some form to fill up and then to justify your reason. Okay, the only reason that the school only accept is actually if you have a visa problem and so on, or your country is still not open to the border. Okay, so that is the only reason for the student not able to come. So the lecturer need to use a hybrid mode. So meaning the hybrid mode, meaning that we still have face-to-face for the student who are inside UTM. We still will meet face-to-face, but for the students that are not able to come to Malaysia, so I need to entertain them. Okay, to attain, meaning that I will only sit on the table and then just uh, write something on my tablet and then display it on the screen LCD and so on. So that is how the hybrid mode will be. And I think for this class we will go for the hybrid because I think we have one or two students not able to come to Malaysia. But it depends on the school decision whether to accept their request or not. Okay. So I am just a lecturer, so I just delay or deliver what the school have what you call have ordered the lectures to do. Okay, so we just follow. Okay, and then good luck for the assignment 1. I have already shared with you in the WhatsApp group the assignment 1. So the assignment 1, the due date is week 14, and as you can see, we have integration of the rectifier and the boost converters, meaning that you are not able to do that until we come to the DC-DC converter, which is the chapter number 3. Okay, but as we are actually moving on that chapter 2, then I think you can try to um, familiar with the MATLAB and so on. Okay, I think that's all. And then please form your own group. Okay, so the same group will be for the assignment number 2, which is chapter inverter. Okay, but that one is very simple and straightforward. The circuit will be given to you, and then what you need to do is just to do some analysis. Okay, I think that's all from me. Any question? So if there is no question, then
No question, Doctor.
okay. So if there is no question, then we dismiss our class. Okay, thank you very much. Assalamualaikum and have a very good day.
Thank you, Doctor.
Doctor.
Thank you, Doctor.